Hello everyone. So, this is the second lecture of this course, and in this lecture I will introduce Gaussian elimination method with partial pivoting. In the later part of this lecture I will discuss about the ill-conditioned systems. Those are difficult to solve using Gaussian elimination method or Gaussian elimination with pivoting. So, in the last lecture we have solved this 3 by 3 system of linear equations using the Gaussian elimination method, and after applying the Gaussian elimination and using the back substitution we got the solution like x1 equals to minus 0.950, x2 equals to minus 2.82 and x3 equals to minus 2.00. However, the exact solution is x1 equals to 1, x2 equals to 2 and x3 equals to minus 3. So, basically there is a big difference in these two solutions, one which we obtained using the Gaussian elimination method and the other one which is the true solution. So, there were some mistake when we apply the Gaussian elimination method or something went wrong. So, procedure were correct, however, the reason for this error is rounding off error propagated to such an extent that the final solution becomes hopelessly inaccurate. So, what is the solution to this problem? The solution to this problem is the Gaussian elimination method with partial pivoting. So, this is a modified version of Gaussian elimination procedure, and here we will search for pivot elements and based on that we will perform the elementary row operations. So, again consider a 3 by 3 system having 3 equations with 3 unknowns, that is a1 3x3 equals to b1. So, this is the second equation, and the third equation is so in matrix form I can write the coefficient matrix as a11, a12, a13, a21, a22, a23 and the coefficient of the third equation. So, these are the 9 coefficients of x1, x2, x3 in all 3 equations, and then if I add the right hand side vector here, then this becomes the augmented matrix. In Gaussian elimination we used to perform elementary row operations on this matrix in such a way this matrix reduce into row echelon form. In Gaussian elimination with partial pivoting, what we will do, first of all we will search for the element having maximum absolute value from the first column. So, I will look for these 3 elements from the first column and I will see which element is having the maximum absolute value, and if this is the element a11 I will not do any operation at this particular moment. If it is a21 I will interchange first and second equation. If it is a31 I will interchange third equation with first equation. After doing this, what I will do, let us assume that the maximum element is A31. So, what I will do, I will interchange my third equation with first equation. So, my augmented matrix will become A11, A12, A13, and here it will come B1, while in this A31, A32 and then A33 equals to B3. So, I have done a operation R1 interchange with R3. So, now this A31 is the biggest element in terms of absolute value in the first column. Now, what I will do, I will make this element as 1. So, what I need to do, I need to divide the first row by a scalar, that is 1 upon A31. So, I need to replace R1 with 1 upon A31 R1. So, what will happen, this element will become 1, this will become A32 upon A31, this will become A31 and it will become upon A31. Now, what I will do, with the help of this first equation, I will make these two elements 0, that is the element in the first column of the second row and element in the first column of the third row. For doing this, I need to perform two more row operations, that is R2 will be replaced by R2 minus A21 times R1 and R3 I need to replace by R3 minus A11 into R1. Please note that this element is now A11 because we have interchanged R1 and R3 in our first operation. So, if I will perform these two row operations, then what I will get, these two elements will become 0 and I will get according to some other values here. So, this is the first pass of Gaussian elimination method with partial pivoting. Now, in the second pass what I will do, I will left out first row and first column and I will perform the same operations in this submatrix in such a way that this entry will become 1 and this entry will become 0. So, here we are changing finally the matrix in row echelon form. However, we are performing some extra operations by searching the pivot elements and we are making the entry 0 with the help of pivot elements at the diagonal position. So, this method is called Gaussian elimination with partial pivoting. So, let us take an example of this method. So, I will consider the same example which I have taken in my previous lecture and for that I got a wrong answer using Gaussian elimination. So, here the same augmented matrix 3 equations with 3 unknowns. So, now in the first operation of Gaussian elimination with partial pivoting, what I will do, I will search the element having the maximum absolute value in the first column. Here you can see the element 11.2 is having the highest value. So, what I will do, I will interchange my first and third equation. This is the same exactly which we have done while I was explaining the procedure. So, here I have interchanged my first and third row. So, this is become my first equation now and third equation will become first equation become third equation. Now, what I will do, I will divide the first row by 11.2 to make the pivot entry as 1 So, what will happen? R1 is replaced by 1 upon 11.2 times R1. So, this will become 1 and subsequently other entry is changed. This is minus 4.30 upon 11.2. So, it is coming out like minus 0.384 and so on. Now, what I will do? I will make this element and this element 0 using the pivot element that is 1 now. So, for this I will replace the second row, that is R2 by R2 plus 1.31 times R1, and R3 I will replace by R3 minus 0.143 times R1. So, after doing these two operations I will get this particular matrix. So, here you can see in the first column, in the first row I am having the pivot entry as 1 and rest of the entry below the pivot elements are 0. So, this complete the first pass of Gaussian elimination method with partial pivoting. Now, what I will do? I will do the same for the second and third equations, but leaving out the first column because these are 0 0 already. So, for this I will go to the second column. In second column I will choose the element having the maximum absolute value out of these two, that is 0.408 and 0.412. So, element 0.412 is bigger than 0.408. So, I will replace third equation, I will interchange third equation with second equation. So, system will become like this. Now, here to make this pivot entry as 1 I need to divide second row by 0.412. So, when I will divide the second equation by 0.412 I get this augmented matrix. So, here pivot element is 1 and then again what I will do? I will make this element 0 with the help of this pivot element. So, what I need to do? I need to replace third equation, that is third row R3 by R3 minus 0.408 times R1. So, after performing this particular operation I got this system and this matrix is in row echelon form. However, if you look at this element, it is not still 1. So, it is a pivot element and I need to make it 1. So, to make it 1, in the third pass I need to divide this equation by this particular number. So, by doing this, dividing the third row by 0.0800, I got this element as 1 and now you can see it is in a triangular form, that it is an upper triangular matrix, or I can say it is in row echelon form. All the diagonal entries or pivot entries are 1. So, from here if I use the back substitution, you can see that x3 will become minus 3, x2 will become 2 from the second equation after substituting the value of x3, and x1 will become 1 after putting the values of x3 and x2. The exact solution is x1 is 1, x2 is 2, x3 is minus 3, which is same which we got using the Gaussian elimination with partial pivoting. Hence, the exact solution agrees with numerical solution, okay, when rounded to the 3 significant digits. So, this is the modification in Gaussian elimination and this particular method called Gaussian elimination method with partial pivoting. Here the term partial in partial pivoting refers to fact that we have chosen the biggest absolute entry in first column in the first pass. So, we are looking only at first column when we are going through the first pass. If we look, instead of searching in first column, if we search it in whole matrix or in second pass like whole 2 by 2 submatrix, then the pivoting or pivoting is called complete pivoting or full pivoting. Unfortunately, we are having some systems where we cannot solve the equation or system of equations using either partial pivoting or complete pivoting. Now, I will talk about some of those systems. So, first of all, I will take the systems, those are called ill conditioned systems. So, some linear systems, those are ill conditioned systems, are extremely sensitive to the rounding off error or any other kind of numerical errors. For such systems, pivoting does not help much. Even though you use partial pivoting, you use full pivoting, we can have a uncorrect solution using the numerical scheme. So, I will illustrate or I will explain such a ill conditioned system with the help of an example. After that, what I will do? I will define matrix norm and I will relate the matrix norm with the conditions when the system become ill conditions, means how to measure whether the system is ill conditioned or it is not. So, let us take an example which is having two equations and two unknowns. So, a very small example, and then we will see that this particular example is an ill conditioned system, example of ill conditioned system. So, let us take first equation as x1 plus x2 equals to 2, and the second equation as x1 plus 1.001 x2 equals to 2. So, here in the matrix form I can write the coefficient matrix as 1, 1, 1 and 1.001 into the unknown vector, that is x1 and x2, and right hand side vector is 2, 2. So, if we solve this particular 2 by 2 system, just looking at this system, we can say the solution of this system is x1 equals to 2 and x2 equals to 0. So, this particular solution satisfies the system of equations and hence it is an exact solution of the system. Now, what I will do? I will not change my coefficient matrix. But there is a little change in right hand side vector. In the entry, right hand side entry of the second equation, let us say earlier it was 2, but it has become, let us say, 2.001 due to some error. It may be some numerical error or some error in the measurement, maybe let us say some sensor error. So, what will happen? I am having a very small change in the input data. Earlier it was 2, now just here it is 2.0001. That is a change of the order of 10 raised to power minus 4. Now, if we look the solution of this particular system, this new system, what I will get? x1 equals to 1 and x2 equals to 1. Now, look at these two solutions and the two systems. In input data, I am having a very little change, a change of the order 10 raised to power minus 4. here it was 2, it is 2.0001. However, if you see the change in the solution, we are having a large deviation. So, if we are having a large deviation in the solution just due to a small change in the input data, such a system is called ill-conditioned system. So, it is a perfect example of an ill-conditioned system. Now, the same example, and this particular example shows that a small change of 0.001 in system of equations makes a significant change in the solution of the system. So, in a system of equation x equals to b, when the solution is highly sensitive to the values of the coefficient matrix A or the right hand side vector b, the equations are called to be ill conditioned. A matrix norm is a real valued function which is defined on a set of, let us say, n by n matrices and satisfying the following conditions. Condition 1, the norm of a matrix will be always non-negative. The second condition is it will be 0 if and only if A is a null matrix or 0 matrix. If you multiply the matrix A by some scalar alpha, then norm of the alpha times A will become absolute value of alpha times norm of A for all alpha belongs to real set of real numbers. The fourth condition is triangle inequality, that is basically if you are having two matrices A and B of order n by n, then norm of A plus B will be always less than equals to norm of A plus norm of B. So, any real valued function satisfying these properties on a set of n by n matrices is called a norm. We are having different types of norm. The first one is natural or induced matrix norm. It is defined for a matrix A by this equation. So, norm of A will be maximum of norm of A times x, where x is a vector in Rn and it is a vector having unit norm, vector of unit length. So, here if you are having a vector of unit length, you multiply this vector with A. So, norm of A equals to maximum of norm of x. The second type of norm we are going to define here, maximum row norm. For any n cross n matrix A, the maximum row norm is defined as norm of A equals to maximum over the absolute sum of all row. Means absolute sum means we are having entries of each row. Let us take entries in first row, take the absolute value of each element of the first row, take the their sum, similarly take the absolute sum of second row and so on, and then maximum out of those sums will give you the maximum row norm. The third norm we are going to define here over the set of matrices is Euclidean norm, and that is given by square root of R of ATA, where R of A is given by maximum absolute value of lambda and lambda is an eigenvalue of A. It means maximum over R of the all eigenvalues in terms of absolute value. Let us take a matrix 3 minus 2 4 as the first row, 1 2 minus 3 as the second row and 2 4 1 as the third row. So, here if you look, the maximum row norm of this matrix, let us say A, is given by maximum of, so in the first row 3, the absolute value of minus 2 will be 2. So, 3 plus 2 plus 4, it will become 9. For the second row 1 plus 2 plus 3, so it will become 6, and in the third row it will become 2 plus 4 plus 1, that is 7. So it is 9. On the other hand, Euclidean norm for this particular matrix will be square root of maximum of eigenvalues of A transpose A. So, if this is the A transpose A will be having the eigenvalues as 3.61, 23.66 and 36.73. So, it means square root of 36.73, which is maximum among these 3 eigenvalues, and these are the eigenvalues of A transpose A, and this is coming out as 6.06. So, here you can see the Euclidean norm induces the matrix norm. Now, to relate these norms with the ill conditioned system, we are having an important result in this theorem. This theorem tells let A be the non-singular matrix, then the solution x and y of the system Ax equals to B1 and Ay equals to B2 respectively satisfy this particular inequality. So, I am having two systems, Ax equals to B1, another system is Ay equals to B2. So, I can write x minus Ay, if I subtract the second from the first, equals to B1 minus B2, or it can be written as A x minus y equals to B1 minus B2, or x minus y equals to A inverse B1 minus B2. It is given that A is non-singular, so A inverse exists. Now, norm of this particular vector equals to norm of this vector, and by the inequality I can write norm of A B less than equals to norm of A into norm of B. So, I can write norm of A inverse into norm of B1 minus B2. So, norm of x minus y less than equals to norm of A inverse B1 minus B2. If I divide it by the norm of x, this will also divided by the norm of x. Now, I can write it the left hand side as such, x minus y norm upon norm of x, this is less than equals to, if I multiply in the right hand side in the numerator as well as in denominator by the norm of A, so it will become norm of A inverse into norm of B1 minus B2 upon norm of A. Since I have multiplied in the numerator, so I have to multiply in denominator also into norm of x. We know that norm of A into norm of x will be always greater than equals to norm of Ax. So, if I replace it, this inequality will not change, and as you know that norm of Ax equals to, here Ax equals to B1. So, norm of Ax will be norm of B1. So, I can replace here it norm of B1, and this is the result of the theorem. Here we can see that multiplying coefficient norm of A into norm of A inverse is interesting. It depends entirely on the matrix in the problem and not on the right hand side vector, yet it shows up as an amplifier to the relative change in the right hand side vector. So, if it will be an higher value, that is norm of A into norm of A inverse for a matrix, there will be a large change in the solution due to a small change in the right hand side vector, and hence what will happen, the system will become ill conditioned. So, based on this idea we can define the condition number. So, for a given non singular matrix A, which is a real having real entries and of size n by n, and a given matrix norm, the condition number of A with respect to the given norm is defined by condition number of A as norm of A into norm of A inverse, means this particular term. So, if condition number for a matrix is large, even a small variation in the right hand side vector, that is in B1 or B2, can lead to a drastic variation in the solution, and such matrices are called ill conditioned matrix. So, if you see the earlier example which we have taken 1 1 1 1.0001. So, this example was taken in the beginning when I introduced the ill conditioned system. So, norm for if this is the matrix M, the condition number of this matrix will be something around which is quite large, and hence the system was the ill conditioned system. So, I will stop this lecture here. In the summary of this lecture, first I introduce the Gaussian elimination with partial pivoting, and in the second phase of the lecture I have introduced the ill conditioned system and the idea of condition number to measure the whether a system is ill conditioned or not. And in the next lecture I will continue with the direct method for solving the linear system, and there I will introduce a technique called LU decomposition. Thank you very much.